on polar graphing equations and coordinates. We're today going to focus on what it looks like to have a polar equation. So just like with graphing, we can look at a graph in rectangular coordinates, then we go back and we expect there are equations with x's and y's that mirror this. And so when it comes to polar coordinates and working with working in the polar system, that also means there are going to be polar equations. In order to build them, rather than just starting from scratch, what we're actually going to do today, which I think it's so fun, is we are going to take rectangular equations that we recognize, that we've worked with, that we've seen before, and use these conversion formulas from yesterday. I've already copied them in. So if you want to go to your notes yesterday and copy these over, or grab a screenshot and drop them into your notes, these are our formulas, which I will review here in just a second, but we're going to use these to make conversions and make substitutions into our equations to put everything into r's and thetas for our polar form. So here's what we have. As a reminder, yesterday, if we have a point r theta, it forms this right triangle, x and y, and off this basis, we came up with these conversion formulas. So we have r squared equals x squared plus y squared. We have tangent of theta equals y over x. And remember, these are mostly helpful when we're going from rectangular to polar for points. For polar to rectangular coordinates, we have x is equal to r cosine theta and y is equal to r sine theta. Now, when it comes to converting equations, all four of these are fair game. They can be useful in different places, and we'll really use a good mixture of all of them. So let's go. So here's what we have. For number 1, we are going to convert each rectangular equation into polar form. So that goal, in order to know that we are done when we are converting into polar form, there will be no x's and y's, so no remaining x's or y's, and our equation will be in terms of numbers, r variables, and theta variables. It might sometimes only have r's, it might sometimes have both theta and r, and then we'll go from there. So we're going to learn how to do it by example. So part A here, x squared plus y squared equals 100. I want you to stop and I want you to think this is a conic section. This is either a ellipse, circle, hyperbola, or parabola. Do you remember, based on our flow chart, which one is which? If you forgot, let's go ahead and graph it. This is x squared plus y squared equals 100, which is a circle, and it has a center at 0, 0, and it has a radius of 10. So now this will help us have a basis as we start to think about what features this had and how that shows up in our polar coordinate. So here's the idea. Our goal is to use the equations above and make replacements. So what I want you to do is kind of like puzzle matching. Do you see something that follows a format that we can make a replacement with? Or we can also always go back to anytime there's an x, we could replace it with r cosine theta. Anytime there's a y value, we could replace it with r sine theta. So here's what I would like you to notice. X squared plus y squared, this feels familiar. We have seen this before. This shows up in the equation r squared equals x squared plus y squared. So that means that we can make a substitution for r squared in the place of x squared plus y squared. So making that replacement, this means that r squared is equal to 100. So that's pretty simple. In one small substitution, I got rid of the x term, I got rid of the y term. The only thing left is a number and r squared. The last thing we want to do is square root this equation so that we solve for, we do want to, like we solve equations for y, if we can, we want to solve this equation for r. So this gives us r is equal to, we do still have our plus or minus 10. So in polar form, a circle centered at the origin with radius 10 is represented with the polar equation r equals plus or minus 10. And when we get into graphing, you'll see how this is represented and how this works. So let's go on to example B, where we add in another layer. X squared plus y squared minus 8x is equal to 0. So here, this is just based on looking at the equation. Again, I have x squared and y squared. Those are both positive. There's no numbers in front. This is going to be another circle, but let's see how this changes. I'm going to make this equal to 0, and then add this minus 8x. And that gives us a circle, but the circle is shifted horizontally. So this is a circle that is translated horizontally. So here is a very useful trick. Whenever you see this duo of x squared plus y squared, the easiest substitution, the easiest combination is this group together is our r squared. So making a substitution, that makes this r squared, and then I'm going to carry the minus 8x equals 0 along for this step. So just to do things one at a time. So r squared minus 8x is equal to 0. So now the last thing we need to do to get it fully in polar form is that x needs to go. It needs a replacement. So at this point, we want to go to the equations that isolate x, and that is x is equal to r cosine theta. So I'm going to replace x now with this equation, r cosine theta. So this gives me r squared minus 8r cosine theta is equal to 0. All right. So now this is now fully in polar form. The x's and the y's are all gone. We only have r's, numbers, and thetas and cosines. So what we're going to do to finish is we are going to do some cleanup work. The work that I show you is a pattern that you will do a lot. And so if it feels confusing, the goal is to try to solve for r. So what we're going to do is, if we notice, both terms have an r in them. The first term is r squared. The second is just r. So I'm going to factor the r out. So this becomes r times r minus 8 cosine theta is equal to 0. What we're going to do next in the process is, with factoring, whenever we factored something, we can take both pieces and set them equal to 0. So this means r equals 0, or r minus 8 cosine theta is equal to 0. Here, r equals 0 just means a circle with radius of 0. That's nothing, so we can ignore that. That is gone. And lastly, the goal, the reason we're doing this is so that we can solve for r. So now I can add 8 cosine theta to the other side. So r is equal to 8 cosine of theta. And this is our equation. So the polar equation for this translated horizontally circle is r equals 8 cosine theta. Okay, all right. So that's the next one. Let's go on to part C. So if you feel slightly confused, a couple things that I want you to pay attention to. First, are you able to successfully make the replacements? That's the step one. If you have difficulties with that, please let me know. That is the first level of skill. The second level of skill is, how do we clean it up? Some of that takes watching examples as we go. The goal being that you are trying to have the equation either r equals something or theta equals something. So we're going to use algebra techniques to do that. Okay, part C. Part C is y equals x. This is going to be a line, y equals mx plus b. This is a line that goes through 0, 0. And this is going to have a slope equal to 1. One last thing to point out, I realize that I'm done so far. The reason we want to get this r equals is so that we can graph them. When you graph in polar form, just like on the calculator, which I will show you later how we graph on the calculator in polar, but when I go to graph, it says y equals. So, oops, hold on, let me quit. Okay, it says y equals. And so you cannot plug something into the TI graph calculator feature unless it's solved for y. When we get to polar, we cannot plug something in unless it's solved for r. So we'll see that here in a bit. Okay, so I want to replace y, I want to replace x. X is equal to r cosine theta, so we can replace x with r cosine theta. Y is equal to r sine theta, so we can replace it with r sine theta. So this gives us For y, r sine theta, and then for x, r cosine theta. Here's a couple of ways that I remember which one is which. X comes before y, alphabetically cosine comes before sine. And then if you know your unit circle, on the unit circle, cosine is the x value, sine is the y. So there's a couple of good ways to remember this. Okay, what I'm going to do now is I am trying to either solve for r or solve for cosine. What I notice is that there is an r that's on both sides of this, and so it's going to eventually go away or cancel out. So what I'm going to do instead is my goal is to solve for theta. So how we're going to do this is I'm going to divide by r cosine theta. So we need to divide by everything on the other side. So now, when I do that, the r's cancel on both sides, and we are left with sine theta over cosine theta is equal to 1. When everything cancels, so the cosines here cancel as well, when everything cancels, it equals 1. What is sine theta over cosine theta? Well, that is tangent. So this gives us the tangent of theta is equal to 1. The reason I did this is because I want to actually solve for theta. And so in doing that, I have to somehow condense those trig functions together. And so this is how we're going to do it. So now to solve for theta, I need to use the inverse. So that means that theta is going to be equal to the tangent inverse of 1. Now is when we would go to our unit circle. Where is tangent equal to 1? And that is going to be at pi over 4. So that gives us solved for either r or theta. R went away, so we couldn't solve for r, so we solved for theta. Theta is equal to pi over 4, which feels crazy, but this is actually an equation. This means that we are going to graph along the polar graph, and we are going to highlight the line pi over 4. And when we get to graphing, you'll see a little bit more how this works. Okay, one other thing is with the unit circle, we do have a couple of other options. We could use all of the angles that are coterminal with pi over 4. So with inverse, we have a couple of options. So we could also use the inverse equals 1 at 5 pi over 4. It also equals 1 at negative 7 pi over 4, negative 3 pi over 4. These are all coterminal with pi over 4 or 5 pi over 4. One last note, theta equals pi over 4. Because it's not r equals something is going to be the only graph that's not possible to plug into a graphing calculator or Desmos and get a graph, but we can do it by hand still. We can still graph this, and the graph of it we know would look like the line y equals x. All right, one more example in this section before we go the opposite direction. Part D, y is equal to x squared. So at this point, because I don't have this x squared plus y squared grouping, we're going to go back to those r sine theta and r cosine theta equations. So y is r sine theta, so let's make that replacement. X would be r cosine theta, so we have to square that. So this would be r cosine theta squared. Okay, so now let's go ahead and square that. That gives us r sine theta is equal to r squared cosine squared theta. And now at this point, I would try to, when you have multiple trig functions, I would use, rather than using addition, subtraction, I would use division to try to turn them into tangents, to try to group them together. And so what I'm going to do here is I am going to divide first by, I'm going to first divide by the r. So I'm going to divide by r, and then those r's cancel on the left, and then cancel the square on the right. So that leaves us with sine of theta is equal to r cosine squared theta. Awesome. Okay, so now we have that. I want to isolate r. And so now to isolate r, all I need to do is divide by cosine squared theta. So I divide by cosine squared theta. And we are left with r is equal to sine theta over cosine squared theta, which I'm going to split right now into cosine times cosine. This will help us remember how to combine these. So what we have here is one of these groups of sine over cosine can become tangent. So this would become r equals, let me do this on another line below, this would become r equals tangent of theta. Let's try to get rid of the fractions just because it looks cleaner. 1 over cosine, that is secant, so this gives us tangent theta times secant of theta. So that one's fun. This doesn't feel amazing, but this is about as good as we can get it because we have to have those two cosines, we have to have the sine, and this is the most condensed, but we did solve for r. And I got so caught up in this that guess what we didn't do? We didn't graph it. What is this? Y equals x squared. That is your parent function parabola, y equals x squared. So for y equals x squared, in order to graph this as a polar equation, it would be r equals tangent theta secant theta. And I promise you it works. If I put that into the proper polar graphing form, that is going to give us a parabola that opens upward with its vertex at the origin. Today, we are going to go the other direction and take a polar equation and convert it to rectangular form. These are fun because if you've started to pick up on the patterns, maybe you see some representations on the circles and how that showed up in equations, but here we have a lot of different pieces that are hard to recognize, and then our goal is to turn it into maybe a rectangular equation we're more familiar with. So let's get into these examples. So for the first example, we have the polar equation r equals 5. So what we want to do is now our goal is to replace any r's or thetas in terms of x's and y's. It might not have both, but it should have some. All right, so how do I make a replacement for r without introducing something else? Well, the most basic equation we have that includes r is r squared is equal to x squared plus y squared. Well, in order to get an r squared, I could take this polar equation and square it, so I have r squared is equal to 25. And then now I can use the r squared is equal to x squared plus y squared and make the replacement that x squared plus y squared is equal to 25. And the r is gone, there is no trig functions, there are no thetas. This is a rectangular equation, so we can put a box or circle around that. This is a circle centered at the origin with a radius of 5. And so r equals 5 polar equation gives us a circle in rectangular coordinates, and it's a circle in polar as well, with a radius of 5. So that's the first example. When you have just a plain r, we can replace that with x squared plus y squared when there's no trig functions around. Part B, we are working with theta. So next up, what we want to do is we have theta is equal to pi over 3. What we found last time when I had theta equals pi over 4, that was a line of sorts. It was the line y equals x. So we're going to expect this to come out to be some sort of line. So here is what we have. It says the tangent of theta is equal to pi over 3. And so currently, I have theta, but I don't have a tangent around it. What I can do is I can make this tangent of theta is equal to the tangent of pi over 3. What I'm doing is I am taking the tangent of both sides. Let me put parentheses around that so it's a little bit easier to see. So let's rewrite that. So we'll add tangent in. The tangent of theta is equal to the tangent of pi over 3. Now I have something that I recognize. The tangent of theta is the same as y over x. So let's make a replacement. That means y over x is equal to the tangent of pi over 3. Now, if you never bothered to learn your tangents, this is going to be tricky. Going to our unit circle, you could also do y over x, but the tangent of the positive pi over 3 is root 3. So this is the tangent of x is the square root of 3. And then with any good equation in rectangular form, we want to solve it for y if possible. And so here, multiply by x, this gives us that y is equal to the square root of 3x. So this is a line with slope square root of 3. This just means the slope is whatever the numerical value of the square root of 3 is. This is y equals the square root of 3x, which is this line right here. Awesome. Okay, and if you look at it, we should expect that line should be about where the pi over 3 line is in the unit circle. Cool connection. Okay, here's our last example we're going to do with going polar to rectangular. Okay, so this is an important distinction. Before, with part A, this involved the r, and it was just r equals 5. Now I have r is equal to negative 5 cosecant of theta. I have introduced a trigonometry function into this. Now, there are certain forms of this that will work out a little bit nicer for us and some that will involve us to be more creative. For the sake of these notes today, we're going to keep it more on the simple level so that they should hopefully work out with nice substitutions without having to crazily convert things. So, here's what we're going to do. The only equations I have that include trigonometry functions are tangent of theta equals y over x, or r equals cosine theta, x equals r cosine theta, or y equals r sine theta. So let's get this out of cosecant theta into a sine or cosine. So this is r equals, and then cosecant is the same as 1 over sine. So this is negative 5 over sine theta. Well, I actually know that r sine theta is y. So I can actually take this and I can multiply both sides by sine theta. And this becomes r sine theta is equal to negative 5. And this is where that nice substitution comes out. The r and the correct trig function work out. If it was like r cosecant theta, we don't have an equation that quite works with that. We'd have to do something differently, but now we do. And so we have r sine theta, that is equal to y. So this becomes y is equal to negative 5. So this is a horizontal line through negative 5. So r equals negative 5 cosecant of theta is a horizontal line that runs through negative 5. So this is it for in terms of the new content today. But in order to get you excited for tomorrow, we're going to do one more thing. And I'm going to show you this is where this unit starts to get super fun. We're going to look real quick at what does it look like to graph a function on polar axes. So since rather than going in a straight line, we're now going in a circular direction, it's going to make it look a little bit different. So if I graphed y equals 2 sine of x, hopefully that you'll remember the sine function. So the 2 in front means the amplitude is 2. So we either go up to 2 or down to 2. The sine function starts in the middle, and one full period is 2 pi. So if this is a full period, we then divide it into 4 pieces. So this is pi. The first line is pi over 2, and then 3 pi over 2. So for this function, we go middle, up to the top, back to the middle, to the bottom, and then back to the middle. So the sine function looks something like this with the amplitude of 2. And so that's what we can expect. It would keep curving in this pattern as we go from here, and it will periodically, meaning it will repeat and follow this pattern. Now is the time. As we get into the next notes, I'm going to show you a lot more with graphing, but I'm going to do a little Desmos show here. So here's what we're going to do. we need to change this to polar. If you look this little circle, it changes this to a polar grid. And if I just typed y equals 2 sine of x, and I need to put it in radian form. Let me change the color real quick. Okay, it will still graph this, but let's change it to r's and thetas. So what we need to do is go into the alphabet. We are going to find the letter R, so R sine, and then I now need to change x to a theta. Here we go. It formed a circle. It formed for us a perfect circle. And we're going to figure out, I'm going to teach you how to do this by hand, but it looks like it goes up to 2, and this is the same graph, just replacing the y with r and the x with theta, but in polar form, it looks something like this. All right, so now we have our first polar graph. This is just the tip of the iceberg. Let's look at one more cool one before we finish. All right, y equals 2 sine of 2x. So let's go back, and for right now, I'm going to hide that. We're going to go y equals 2 sine of 2x. So it should look pretty much the same, but here is what's happening is it's just making the period, it shortens the period down to pi. So rather than it having a period of 2 pi, it will grow twice as fast. So if at 2 pi we're out here, I'm going to break it so that we can kind of see this. It will have a full rotation by the time we get back to pi. So this is a crash course in this, so we'll go up to the top, back to the middle, down to the bottom, and we'll land in the middle. And then we'll do that one more time. So it will look something like this. So it should be growing twice as fast. So that looks pretty easy, it's just a little bit more squished. How does that change the polar graph? This is where it gets fun. So I'm going to change it to polar, and I'm going to hide this graph, and then we are going to make this 2 sine of 2 theta. Oh, look at that. This is what the graph of 2 sine of 2 theta looks like. And this is why polar graphs are so fun, because they can make some of the craziest, coolest shapes. And this is just a teaser for next week, because we're going to do so much fun stuff with these graphs. So rather than, I'm not going to draw this one on there today, but this will show us what this looks like. So get excited for next week. And here's what we got from here. There is the 9.3 practice is linked in the packet for this week. So if you want to go and complete that, come to office hours, let me know what questions you have, and we'll go from there. All right, that is it.